Good morning. This is Engineering Statistics and Linear Algebra 18 EC44, Module 4, Lecture 8, Linear Transformation. I am Dr. Nurullah Sharif, Professor and Head, CCAB Institute of Engineering and Technology. Let us begin with what corresponds to the transformation. Suppose X is a n-dimensional vector. Then if you multiply this X with the A matrix, the A matrix might be a rectangular matrix which corresponds to m rows and n columns. It transforms that vector into a new vector Ax. If you multiply A with X, it transforms into a new vector Ax. This happens at every point X of the n-dimensional space Rn. So if X is within the n-dimensional space Rn, for all the points in that, will get transformed into another point X dash, which will be in the space Rm. The whole space is transformed or mapped by the matrix A. So, and that is shown over here clearly. So you can see that this is a matrix which has m rows and n columns, and we are multiplying this with a what you call X term, which consists of n columns. That means it is in the space of Rn, and that gets transformed into X dash, which is having m rows. So that will become naturally the m-dimensional space rather than n-dimensional space, right? So in the same way, you can, if you write the other way around, that is, if A is n cross m, then naturally it will do the other thing. Now this can be, the linear transformation has certain properties, and that we'll try to consider over here, how that those can be represented by different matrices. Now you can have a point which is xy in the column, and that if you multiply by the matrix A, which is C0, 0, C, then that will lead to C0, 0, C is nothing but A equal to Ci, where I is 1, 0, 0, 1, which is the identity matrix. So A is becoming this. If you multiply A with a xy, a column matrix with x and y elements, then that gets transformed into Cx and Cy. So that means C into x plus 0 into y will give Cx, 0 into x plus C into y will give Cy. So Cx, Cy will become the new column matrix. And that gives us that we are just trying to multiply each of the term x and y with C. And that is what is mentioned here. If you have xy, and that can be represented in a column matrix as xy, that is transformed into Cx, Cy. The second one is the rotation of the matrix, which turns the whole of the space around the origin. This example turns it into 90 degrees. For example, if you multiply this matrix A, which is 0, minus 1, 1, 0, with xy, then 0 into x plus minus 1 into y will give us minus y. 1 into x plus 0 into y will give us x. So the column matrix will become minus yx in place of xy. So xy gets transformed into minus yx. Here xy gets transformed into Cx, Cy. Here xy gets transformed into minus yx. And that can be represented over here. Xy will be naturally here, and minus yx will be here. So 90 degrees transformation will convert this like this, right? So it is going to become like this. Then we have the reflection matrix. The reflection matrix will be the one which we are considering here to be one which is reflecting. A mirror is supposed to be at 45 degrees, and that is the one which is trying to reflect the normal XY point to a YX point. So this gives you the 45 degrees, line at which the mirror is supposed to be placed. And if you have XY, naturally that will become this point YX. So the matrix which transforms this XY to YX will be this, because if you have XY over here, the column matrix XY over here, which is represented by this represents rather the column matrix XY. Then 0 into X plus 1 into Y will give me Y, and 1 into X plus 0 into Y will give me X. And that is what is this, a column matrix which is represented, which is represented for this point. YX will be Y first and X below that. So the example is given over here for the same. If you have, say, a point which is 2, 2, then that will get transformed into 2 and minus 2. Then that will get transformed into minus 2 and 2, which will be 90 degrees uh, shift. Okay. Then we have the projection matrix, which will, if you have a what you call point, which is known as XY, it's X projected. That is, this point, if it is projected onto the x-axis, then the value of y is going to become equal to 0, and the value of x is going to remain same. So to transform this into this, we need a matrix of this sort, wherein if I put xy here, then multiply with a, then I'm going to get 1 into x plus 0 into y, that will be x, and 0 into x plus 0 into y, that will be 0. So x and 0, and that x and 0 is the one which is over here. So this matrix A is going to transform a point which is xy into x0. So uh, this matrix is going to transform a point xy into cxcy. This matrix is going to transform a point which is xy into minus yx. This matrix is going to transform a point which is xy to yx, which will give us the mirror to be placed at 45 degrees. And this matrix will transform a point which is xy to this point which is x comma 0. So on the whole, we can have a set of rules which should be obeyed by the transformation for it to be linear. So transformations that obey rule 1 and 3 are called linear transformation. And what are these? So the first one is, it is impossible to move the origin, since if you multiply A with the 0 vector, origin or 0 vector, then we'll get a 0 vector itself. So transformation, that is multiplying any matrix A with 0 will always lead to 0. So therefore, it's not possible to transform the origin or move the origin at any other place. If a vector x goes to x naught, then the another vector which is 2x, which is the multiplication of x by 2, must also go to 2x0. That means if what you call, if we shift the x, if you multiply the x, if you transform the x into 2x, then x naught also gets transformed to the 2x naught. So in general, cx must go to cx naught. That means if you multiply x with the c, then x naught also gets multiplied by c, since a of cx is equal to c multiplied by a of x. The third one is, if the vector x and y go to x naught and y naught. If we have two vectors x and y, and if they go to x naught and y naught, then their sum x plus y must go to x naught plus y naught. And that is because of the summation property. This is the multiplication by a constant property, and this is a summation property. Or addition property, a into x plus y is equal to ax plus ay. So combining all these three over here, we will get the what you call for different numbers, number constants c and d, and for vectors x and y, the what you call matrix multiplication must satisfy the rule of linearity, which is a multiplied with the cx plus dy will give us c multiplied with ax plus d multiplied by ay. So this is the rule of linearity which should be satisfied uh, by the linear transformation. So every transformation Tx that meets this requirement is the linear transformation. So whatever transformation of this type will, uh, which satisfies this, that will be the one which corresponds to linear transformation. So please remember that a transformation need not go from Rn to the same space Rn, and that's what really happens here. You can see here x, which is in the n dimension, will get transformed into x dash, which is in the m dimension. So it's absolutely permitted to transform a vector Rn. So that means a vector with in Rn, that is x n, two vectors in a different space Rm, and that is x, so to say, m cross 1. So x dash is a vector with m, so to say, rows in it. That is exactly what is done by this, m cross n matrix, and that's what we have just discussed. The rule of linearity is equally satisfied by the rectangular matrices. So we have a rectangular matrix here, and the rule of linearity will be satisfied by the rectangular matrices as well. So they also produce linear transformations. So rectangular matrices also produce the linear transformation. Vectors in a transform need not be column matrix. We need not have only column matrix. They can be polynomials. They can be matrices, any type of matrices, or they can be functions. So let us consider the polynomial space here, a space Pn in which the vectors are polynomial of degree n, and that can be represented by P is equal to a0 plus a1t plus a2t plus dot 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 plus an tn. So this, if you see a0, a1, an, there will be n plus 1 terms. So the dimension of the vector space is n plus 1 because including the constant, there are n plus 1 coefficients. So we will have a0 to n plus 1 coefficients. Therefore, the vector space here corresponds to n plus 1. Now let us take example corresponding to this. The operation of differentiation on this polynomial is what we are trying to consider. So the operation here is differentiation, that is a is nothing but d by dt, and that means if you take the d by dt of this, then that we consider as transformation in the function p into ab. So a p of t, because it's a function of t over here. So t is the what you call independent variable here, and p is the dependent one. And if you try to take the differentiation of this thing over here, then we are going to get this, because d by dt of a0 will be 0, d by dt of a1t will be a1, d by dt of a2t square will be 2a2t, and d by dt of an t to the power n will be n an t to the power n minus 1. So here, if you see, we have, a1 to an, a1 to coefficient here corresponding to n. So now this polynomial is reduced to the dimension, which is n. So that just means this belongs to the vector space, which is of the order of n rather than n plus 1. So that just means that this is a space which corresponds to Pn minus 1 rather than n. So the null space of this A is a one-dimensional space of constants. That means because d by dt of A naught is equal to 0, the null space here, the A naught term vanishes, and that's why we say that the null space of this is a one-dimensional space of constant. A naught is removed from the what you call transformed value. The column space of A is a n-dimensional space Pn minus 1, because this now becomes here, the dimension of this becomes Pn rather than Pn minus 1 rather than Pn. The right hand side of the equation 2 is always in that space. So whereas A naught to An Tn, that is P, is in Pn, the A1 to dot 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 n An to the power of n minus 1 will be in Pn minus 1. So the sum of nullity, the dimension space for null space is 1, and the dimension space for the column space is n. So 1 and rank n is the dimension of the original space, which is Pn, which corresponds to n plus 1. The dimension of this is n plus 1. Let us take another example which corresponds to the integration of whatever polynomial we have considered earlier from 0 to t. We see that this is also linear, because now AP will become integral of whatever polynomial we have considered A naught plus A1t plus A2t square plus dot 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 ANT to the power of n dt. So now this constant here, if you integrate this constant A naught, then you'll get A naught t. Then the second term might be A1t, and if you integrate that, you'll get A1 t squared by 2, and so on. And if you integrate A and t to the power of n, then you'll get an t n plus t to the power n plus 1 divided by n plus 1. So there is now we can see very clearly that there is no null space now except for the 0 vector, but integration does not produce all polynomials in n plus 1, because of the reason that we always have the initial constant. We don't have a constant over here. We have only the coefficient of t. Here we have a constant, then a1 will be the coefficient of t, similarly n will be the coefficient of tn, whereas here we don't have a constant, only coefficient of t squared, t cube, and till t to the power of n plus 1. So because there's no constant term, we say here that integration does not produce all polynomials in Pn plus 1. Now let us take another example, which is multiplying this polynomial by another polynomial, which is 2 plus 3t. This again will lead to a linear transformation. So now A of pt is equal to 2 plus 3t with the original polynomial which you have considered earlier, that is a naught plus a1t plus dot 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 plus an t to the power of n. And now we will have 2 of a naught, that is 2 multiplied with all this, and then 3t multiplied by all this, and then we can club the equations, the terms corresponding to the coefficient of the constant, and then the coefficient of t, and then coefficient of t squared, and so on. Then you'll get the first term to be t a naught, and so on. The last term to be 3a n t to the power of n plus 1. The coefficient of t here might be, here 2 into a1 will be the coefficient of the first t, and then 3 t into a naught also will be 3 a naught t. So that will give us 3 a naught plus 2a1 will be the coefficient of t, and that will come out as the second term over here. Again, this transformation is from Pn. This is Pn to Pn plus 1, because this will have n plus 2 terms. This is having n plus 1 terms, and this is having n plus 2 terms, which is similar to the integration. with no null space except at p equal to 0. So we don't have any null space here because the A0 term exists over here. Okay, the A0 term will exist over here, and we don't have any null space over here. Okay. Linearity is the most important properties the transformation can have. However, many transformations might not be linear. For example, if you square a matrix, that means take p square, and that we say that it's a transformation AP, then that will not lead to a what you call uh, linear transformation. Similarly, adding 1, that means if you add to p a value 1, then that will not give us a linear transformation. Similarly, taking the modulus of a quantity, turning a negative value into positive and keeping the positive as it is, that will be a of t minus t square. That might give us the minus t, keeping the positive coefficient only. Might will not give us a linear transformation. So we see that only linear transformations can be represented by the matrices. The nonlinear transformations cannot be represented by the matrices. With this, we come to the end of the lecture today. We'll take up the how we can represent the linear transformations by matrices in more detailed way in the next class.